So we have this simple equation, two simple equations for the damping factor, which is in the textbook. And we know the length, we know the viscosity, and we know the density of water, inner radius, and this is just the reciprocal of the, I think this is the modulus for the what's it called? Diaphragm. This is modulus for diaphragm that's specific for each transducer or the catheter, and which this ED is defined as, the unit is delta P over delta V, but because it's a reverse, that's why it's reciprocal of reciprocal. And if you put the actual number in, which is fairly straightforward, the 0.0007 Pascal per second over inner radius of 1 millimeter. So I'm going to use 1 10 to the negative third meter cubed, and then length is 2 meter 2, and then reciprocal of the ED, which is 0.49 10 to the power of 15th, and pi times density, which is 1000 kilogram per cubic meter. If you solve this out, you should get something like 0.0032, and that is the damping factor. And second part, what's the undamped resonant natural frequency, which is R over 2, 1 pi, length, and delta P over the density, delta V, all one squared, not squared, but square root of that. So if you put the actual numbers in, so inner radius of 1 millimeter, 1 over pi times 2, which is the length, and then 0.4910 to the power 15 over density of water, 1000 kilogram per cubic meter, over 2, and then we should get something like 140 hertz. And what it's going to look like is, so this is the frequency, and at 140 hertz, it's going to look something like that. And what we're trying to, the blood pressure resonant, the frequency goes only, for human it goes up to 50 hertz. So it should be fine for us to use this fluid filled catheter to measure the blood pressure.